Greetings. Welcome to week 4 of control systems. And today we'll be discussing a couple of questions. First one is regarding the second order system. So, we want to find out the natural frequency, the damping ratio, rise time, peak time, maximum peak overshoot, and settling time. The given system is y double dot of t plus 3 times y dot of t plus 9y of t is equals to u of t. So we will take Laplace transform and substitute zero initial condition. That results in s square y of s plus 3 into s y of s plus 9 times y of s is equals to u of s. So taking y of s common, results into this. So the transfer function, say g of s, is y of s over u of s, which is 1 over s square plus 3s plus 9. So let me write g2 of s, which is transfer function of a general second order system. It's omega n square over s square plus 2 zeta omega n s plus omega n square. So if we look at the denominator polynomial and compare, we can see that omega n square is equals to 9 and 2 zeta omega n is equals to 3. So this results in omega n equals to 3, and when we substitute it here, this gives us zeta equals to 0.5. So since zeta is less than 1, this implies the given system is an underdamped system. So what is an underdamped system? An underdamped system will have a response something like this, say time and y of t. So if you give a step input and it is supposed to reach here, so then an underdamped system's response would be something like this, which is oscillatory in nature, and it eventually will try to settle down at the uh, given input value here. So there are, on contrary, when this zeta is greater than 1, it is an overdamped system. So an overdamped system would behave something like this. Now it is important to distinguish between the two responses. So when we are looking at an underdamped system, there are certain attributes such as rise time, that is when the system reaches to the steady state output value for the first time, the peak time, that is the time at which the response value peaks out, and the maximum peak overshoot, how much are we overshooting from the steady state value. And finally the settling time. So when are we settling down in the region, uh, that is, when are we settling down to the final value. So there are various notions, and we are going to find out these things. So this omega n is called the natural frequency, and this zeta is called the damping ratio. So let's take a general second order system and quickly try to uh, derive the expressions for rise time and peak time. So if we take unit step response, UFS would be 1 over S. So the output would be omega n square divided by S square plus 2 zeta omega n S plus omega n square bracket S. So if we do partial fractions, we can write it as A over S plus some B into S plus C over S square plus 2 zeta omega n S plus omega n square. So if we multiply on the both sides by S and substitute S equals to 0, we would get an expression for A. So let's substitute S equals to 0. This first S would get cancelled, and substituting S equals to 0 in rest of the cases would lead us to have omega n square over omega n square is equals to 1. So we got value for A, that is 1. Now let us substitute S is equals to positive 1 here on both sides. So here we will be left with omega n square over S square plus 2 zeta omega n. Sorry, so we are substituting S is equals to 1. So we will be left with 1 plus 2 zeta omega n plus omega n square is equals to, this is 1 plus B plus C over the same denominator. So if we do some algebra and take this cross multiply here and add to B plus C, and then we can cancel out the denominators since there is a common denominator. We can write omega n square is equals to 1 plus 2 zeta omega n plus omega n square plus B plus C. So this would get cancelled and would finally result into an equation in B plus C, which is equal to minus 2 zeta omega n minus 1. Similarly, when we substitute S equals to minus 1, we will get here omega n square, and since there is an S term here, we will get a minus sign over 1 minus 2 zeta omega n plus omega n square. So S was minus 1 minus B plus C over the same denominator. So here when we cross multiply, we get minus omega n square equals to minus 1 plus 2 zeta omega n minus omega n square minus b plus c. So this omega n square would get cancelled and we'll have an expression for minus b plus c. So this would be minus 2 zeta omega n plus 1. So if we add the two expressions we have, this one and this one, if we add both of them, we get expression for c, that is 2c is equal to, the plus 1 and minus 1 would get cancelled, 4 into zeta omega n implies, there is a minus sign there, implies c is equals to minus 2 zeta omega n. And similarly, when we plug the value of c in, say, this expression, we'll get b to be minus 1. So now coming back to the unit step response, it's 1 over s minus s plus 2 zeta omega n plus omega n square. So we'll split this 2 zeta omega n into two portions. And we also will define omega d, that is damped frequency, as omega n square 1 minus zeta square. So using this, we can write this s square plus 2 zeta omega n s plus omega n square as s plus zeta omega n whole square plus omega d whole square. And similarly, we'll have minus zeta omega n over omega d square. So here what we can do is, we can multiply by omega d and divide by omega d. So if we substitute this omega d, say by omega n under root 1 minus zeta square, then we can cancel this as well. So the final expression can be written as 1 over s minus s plus zeta omega n over So if we observe these terms, we can see that this term is looking something like Laplace transform of a cosine term, and this is looking as a Laplace transform of a sine term. So the y of t is essentially 1 minus e power minus zeta omega n cos of omega d into t minus zeta over 1 minus zeta square sine of omega d into t. Now that we have an expression for the output for the step response, we can figure out the rest of the quantities. So we are interested in finding out what is the rise time, then what is the peak time, and what is the maximum peak overshoot. And finally the settling time. So as we discussed, rise time is the time at which rise time is the time at which we reach the steady state output for the first time given a step input. So let's find out what is y at infinity. So since there are exponent terms, e power minus zeta omega n t. So yeah, since we have the exponent terms here and here with the negative coefficient, as time t tends to infinity, this would go to 0, this term would go to 0. So y of infinity would be 1. Hence, when we equate y of t equals to, so for rise time, let's call that as tr is equals to 1. This would give us condition e power minus zeta omega n t in bracket to be equals to 0. So here, since the exponent term only asymptotically goes to 0, the bracket term should be 0. This implies so yeah, since I have taken minus sign common, it will be plus cos of omega dt equals to minus zeta over 1 minus zeta square sine of omega dt. So if we write tan of omega dt, and since we are solving for rise time, this is tr is equals to minus under root 1 minus zeta square over zeta. So if we take tan inverse, we can write TR as 1 over omega d tan inverse of minus under root 1 minus zeta square over zeta. So in classroom, if you remember, we would have also done a definition of beta such that cos beta is equals to zeta. Then tan beta would be defined as omega d over zeta omega n, which is essentially under root of 1 minus zeta square upon zeta. So if we want to use this, no, if we want to figure out tan inverse of minus under root 1 minus zeta square over zeta in terms of beta, so this entire term would become pi minus beta since there is a negative sign. So this is the expression for rise time. In the given case, zeta was 0.5. This implies beta or cos beta is 1 half. Since cos beta is 1 half, beta is pi by 3. So when we substitute here, the rise time for our given problem turns out to be pi minus pi by 3 over omega d, which is omega n, that was 3 under root 1 minus 0.5 square. So this expression uh, evaluates to 0.8 seconds. So this is the rise time. Now coming to peak time, we can take this expression and differentiate with respect to time. When we differentiate this with respect to time and set it to 0, we will be looking at an extrema. Now this extrema can be a minima or a maxima. So to ascertain whether the minima is whether it is indeed the minima or indeed maxima, we would also need to take second derivative. So if we do dy by dt and set it to 0, Yeah, so if we do dy by dt and set it to 0, we will end up getting a condition as sine of omega dt is equals to 0. This implies the solution is all the times when we are reaching 0. So the peak time would be of the form n pi by omega d. So since we are looking, hello, yes, yeah. So the peak time would be of this form, and we need to figure out n. Since we are looking at the time when we will be reaching at uh, the peak would be reached at only at the first time instance. Yes. So the peak would be reached as per the response only for the first time, as it will die down and settle down to the steady state value. We will choose n equals to 1, and then the peak time is essentially pi by omega d. For the case we are studying, omega d is 3 under root 0.75, which evaluates to 1.2 seconds. Now that we have peak time, we can substitute the peak time uh, into y and find out the value of peak. So if we do that, the maximum peak overshoot, say given by mp, is y of tp minus y at infinity over y at infinity, and is generally given in percentage, so we can multiply this by 100. If we substitute and solve, the expression evaluates to be e power minus zeta pi over under root of 1 minus zeta square. So for our case, if we write mp is equals to e power minus, say, zeta was 0.5 into pi divided by under root 0.75, this expression this would essentially result in 0.163. So the maximum peak overshoot is 16.3%. If you notice, the expression for maximum peak overshoot is only dependent uh, on zeta. Let me write it clearly. So depending upon the value of zeta, this maximum peak overshoot can be adjusted. And uh, finally, the settling time. To evaluate settling time, there were two criteria. We'll be looking at 5% criteria and a 2% criteria. So if we see this expression for y of t, this will reach to the steady state value only asymptotically. right? That is when time t tends to infinity. However, when we define settling time, we are saying that if we are say within 2% or within 5% of the steady state value, uh, and if we have reached in that band for the first time and given no change in state, no change in the input, we would stay in that band forever. Then in such a case we can say that the output has settled. So for the 2% criteria, it is TS. The settling time comes out to be 4 over zeta omega n. And when we substitute the values, so zeta is 0.5 and omega n is 3, this comes out to be 2.67 seconds. So if we draw this and say this was the steady state value, so this is the rise time, we are reaching here in 0.8 seconds. This is the peak time, we are reaching here in 1.2 seconds. And this peak value here is 1.163, that is the peak overshoot we are counting for. And say if we draw a 2% band here, we are reaching here for the first time and staying there after 2.67 seconds. Uh, yes, so uh, coming to the second question, we are considering a second order system that is governed by this differential equation. We have to do the following: comment on the stability of the system, and then we'll have a proportional controller, and we'll design a unity negative feedback closed loop system. We'll find the range of Kp for which the system would be stable. And finally, we'll find the state error in tracking a unit step input. So let's start here. So I'll directly start with taking Laplace transform s square y of s, and we'll also substitute 0 initial condition, so that we get s into y of s plus y of s is equals to u of s. The transfer function g of s is y of s over u of s. So let's look at poles. S equals to, so let's apply the quadratic formula, minus b plus minus under root b square minus 4ac over 2a minus half plus minus under root 3 by 2 iota. So we have complex poles, and both of them are in the left half of the complex plane. This implies the system is stable. Now let's take this and make a unit feedback controller. So we have a proportional controller, say C of S, So let's draw a closed loop block diagram. Here we want to find y of s over r of s. So let's quickly start substituting. Y of s equals to g of s into u of s. And then u of s is c of s into e of s. Then e of s is r of s, and let's call this w of s as we did in last session. R of s minus w is h of s into y of s. So if we take this term on this side, we will get y of s in bracket 1 plus g of s, c of s, h of s is equals to g of s into c of s into r of s. So the closed loop transfer function is g of s, c of s over 1 plus so since it is unity feedback, h of s is equals to 1. Since it's a proportional controller, c of s is equals to kp, and g of s we already know. So let us substitute these things to obtain the closed loop transfer function. Kp over s square plus s plus 1, and in the denominator 1 plus kp over s square plus s plus 1. So if we solve the denominator and cancel out the s square plus s plus 1 term, we will be left with kp over s square plus s plus kp plus 1. This is the closed loop transfer function. Now what has been asked? Find the range of kp, that is the proportional gain, for which the closed loop system would be stable. So let us find the roots of closed loop transfer function. Sorry, the poles of closed loop transfer function. So minus 1 plus minus under root b square, that is 1 minus 4 into kp plus 1 divided by 2. So the system is stable when the closed loop poles are uh, in LHB. But for the second order polynomial, if all of them are all of the terms are positive, all of the coefficients, that is say one here, one here, and this term, if all of them are positive, then the poles would be uh, in the left half of the complex plane. So if our Kp, alright, let's test that idea. So let's look at this expression for poles and see when can the poles be in RHP. So say if Kp is greater than so if Kp plus 1 is negative, that means if Kp is less than minus 1, as per what I just said, that the coefficient should be all positive, the pole should be in RHP. Let's test that value idea here. Let's take Kp as minus 5. So S would be minus 1 plus minus under root 1. So we have minus 5. Minus 5 plus 1 would be minus 4. We have 4 here. So plus 16 by 2. So we will have a term minus 1 minus under root 17 over 2, which is negative. But we'll also have another term minus 1 plus under root 16. Sorry, under root 17. So under root 17 would certainly be something greater than 4. So when we subtract 1 also from it, it will be something which is positive. So if Kp is less than minus 1, in this case, the closed loop system would be unstable. So one important thing we can take from this problem is that even though the original system was a stable system, right, the poles were in LHP, sometimes the closed loop controller, if not tuned appropriately, can result into the closed loop unstable system. I think we should always remember these kind of things. Let me note it down here. In certain cases or situations, a stable system may become an unstable closed loop system if the controller is not tuned properly. So what do I mean by controller tuned properly then is ensuring that your closed loop system is stable. So Kp less than minus 1 for stability. Oh, sorry. Kp greater than minus 1 for stability. Since here Kp minus 1 would result in the poles being in RHP. Now coming to the third part, find the steady state error in tracking a unit step input. So let's write say I'll write GCL as closed loop. So The transfer function is kp over s square plus s plus kp plus 1. So we want to find out y at infinity. So we'll use the final value theorem again. This becomes s tending to infinity y of, sorry, s tending to 0 y of s. S into y of s. So we have the first s coming from final value theorem, and then since we are taking unit step, there will be this 1s. This s would get cancelled, so we can directly substitute the limit here. Y of infinity would become kp over kp plus 1. So just using a proportional controller, we will not be able to reach to the final value. So what was the input given to the system? We gave a step input and we wanted value to be 1. Alright, and if say kp we are considering to be some value which is greater than -1, say consider kp is equals to 2, this will ensure stability of closed loop system. The steady state value would be 2 over 2 plus 1, that is 2/3, roughly 0.66. So this is what we gave, and the system settles down to this value. Okay, and so this is called as steady state error. So I think that ends my tutorial for today. We can have any questions from the audience. All right, thank you, Saurav. Uh, I hope at least from today's discussion you can take this point written in orange with you as a valuable outcome. So if there are no further questions, we can close today's session.